Hello everyone. In this video, we are going to be going over Kosaraju's algorithm. What does this algorithm do? The goal of this algorithm is to find strongly connected components within a graph. What are strongly connected components? We can see in the subgraph, I can explain. A goes to B, B can either go to D or C. We'll just choose C for now. C goes to D, and D goes all the way back to A. This is called a cycle, and all cycles within a graph are considered strongly connected components. So that is one example. So we're going to go through the algorithm and see how does it work. So we're going to choose any vertice within this graph. For my convenience and organization, I'll just choose A. So we're going to start at A, and we're going to label the numerator of A with 1. Now, we're going to check what is A's neighbor. We can't say it's D because A doesn't want to go to D because of the arrow. So A wants to go to B. And since B is the next neighbor, we're going to label the numerator with 2. Now B can either go to D or C. It really doesn't matter. You can choose D, but for just convenience and organization, I will choose C. So now that we label C with 3, we're going to see C's neighbor. It is D, only D, so we can label D with 4. Now, D can either go back to A or it can go to E. We're going to choose E because A has already been visited. So we have to choose a vertice that has not been visited yet. So D can go to E. So we're going to label this 5. E can either go to F or G. Again, it's your choice for organization. I'm going to choose F. F can go back to C, but C has already been visited. So F can't go anywhere else. This is a dead end. And when we have a dead end within the vertice, we're going to label the next number in the denominator. And then we're going to push the vertice F into the stack. Now, after we reach a dead end, we have to backtrace to the most recent vertice we visited, and that was E. Now, is there anywhere E can go that has not been visited yet? Yes, there is G. G has not been visited yet, so we're going to visit G. G can go back to F, or it can go to H. But like I said, F has already been visited, so we're going to visit H. H has absolutely nowhere to go, so this is another dead end. We're going to label it the denominator with the next number, and we're going to push H onto the stack. So we have F, we have H. Now we're going to backtrack to G. Is there anywhere G can go? No. So this is another dead end. We're going to label the denominator with 11, and we're going to push G onto the stack. Now we're going to do another backtrack. Where did G come from? G came from E. Is there anywhere E can go? No. So we're going to label it with 12 and push it onto the stack. We're going to backtrace. Where did E come from? E came from D. Is there anywhere D can go that hasn't already been visited? No. So we're going to label it 13 and push D onto the stack. And you can already see where this is going. There's a pattern going along. Backtrace back to C. Anywhere C can go? No. 14. Push it onto the stack. B. 15. Push it onto the stack. And then lastly, A. We're going to label it 16. And then we're going to finally push that last one onto the stack. So that is the first part of tracing a graph using Kosaraju's algorithm. Next, we will go over the next part of this, finding the strongly connected components. And in order to do this, we have to reverse the directions on our graph. All right, I have switched the directions of the graph. Now we need to perform the same DFS algorithm that we did in the previous step, but there are some rules. The first rule is that we have to go in the order of the stack when we visit our vertices. So what is the first vertice we have to visit? We start at this top element and it is A. So the first thing I'm going to do is create a list of our visited vertices. And we're going to pop A from the stack. So A is no longer in the stack. And we're going to visit it. We're going to put it in our visited list. Where can A go? A can only go to D. So D is going to be in our visited list. D goes to C. C goes in our visited list. C goes to B, goes in our visited list. B goes back to A, but A has already been visited. So that will end this cycle. So we're going to create a list of our strongly connected components. Our first one is A, D, C, and B. These elements of this list form their own strongly connected components. So now since we visited D, C, and B, we can just pop them off the stack. We don't need them anymore. So we're going to pop, pop, and pop. Say pop. All right. So what's next in the stack? E. So we have to visit E. Where can E go? E can go to D, but D has already been visited. So this is our dead end already. So we have visited E. We have popped it from the stack. And now we create its own list. And it is okay to have singletons. So E is its own strongly connected component. What's next in the stack? G. We have visited G now. G can go back to E, but E has already been visited, and it can't go anywhere else. So we need to create a singleton list with just G and pop it. We go to H. H can go to G, but G has already been visited, so it's its own singleton again. And pop it from the stack. Lastly, we have F. F has already, so E has already been visited, G has already been visited. So that is another singleton list. And we pop F finally from the graph. So this here is our strongly connected components within the graph. We have created a number of lists representing our strongly connected components. And that is what the algorithm does. So now we need to analyze the time complexity and space complexity. So the time complexity is big O, is every vertex in every direction added together. So it's V plus E is our time complexity. Our space complexity, we're using a stack of only vertices, which is linear. So we're going to do O of V for our space complexity. So now you know how Kosaraju's algorithm works, and you can perform this traversal by doing these steps.